Okay, welcome to a podcast that's interested in finding derivatives involving all four of these functions, which are now in play, relative to these kinds of rules. So let's take a look at a classic kind of an IB question, where given something like y is equal to e to the 2x times sine x, can you show the second derivative is equal to this form that you see here? Of course, dy dx is the first derivative, and d2y dx squared represents the second derivative. You need to be aware of that notation. And this is a classic kind of an IB question where you're asked to find the parameters a and b, where they're indicated as integer values. There are values to be found, and then once you find that, hopefully you can extend it to answer the following question there. So let's have a look. So you can see that firstly we're going to say, okay, given this is the function in play, first derivative demands the product rule, where you've got first times derivative of the second. Derivative of sine x is, of course, cosine x, plus the second, which is sine x, times the derivative of the first. And it's your job to recognize that not only is the derivative of e to the 2x itself, but it's further times the derivative of that piece inside. Chain rule is hiding in there in terms of differentiating that particular piece of the function. And so e to the 2x is a common term between this term here as separated from this term here. So if we factor out the e to the 2x, we're left, of course, with cosine x plus the 2 sine x. This is arguably a better form of the first derivative from which to proceed in terms of getting the second derivative. You don't have to do this. You could differentiate each of these forms separately to get the second derivative, although you would find that the problem will grow on you algebraically. So second derivative relative to the first, I need the first, which is e to the 2x, times the derivative of the second. Well, the derivative of the second is just the separate derivatives of each of those. Derivative of cosine of x is negative sine x, and the derivative of 2 sine x is just 2 cosine x. So that's the first part, namely first times derivative of second, plus the second, all of this, times the derivative of the first, which once again requires you to employ the chain rule. And so at this stage, you're then saying, okay, there's lots going on here. I'm trying to drive it into this particular form here because that is the form that's required. You are ultimately trying to get yourself to a and b. And if you can recognize that there is the common term of e to the 2x once again, and again, just to remind you, all of this represents one term plus all of this, which is your second term. So these two terms share in common e to the 2x, and when you factor it away from this first term, you're left with this piece here, because e to the 2x times all of that would give you this back. And when you factor it away from here, you need to be a little bit careful, because there's this 2 in here that's multiplying by each of these, and that's why you see the 4 and the 4 and the 2 respectively in here. Again, e to the 2x times this would give you this whole thing back. So now all of these like terms, if you will, can be cleaned up. So 4 of these minus 1 of those is, of course, 3, and 2 plus 2, where I come from, is 4. Hence, a is 3 and b is 4. Once you know that, to answer the second part, you're letting all x be 0, because that was the request. And it's your job to remember a couple of particulars here, namely that e to the 0 power, like any base to the 0 power, is 1. This, of course, just zeroes out because the sine of 0 is 0. And this one's a little bit slippery sometimes, too. The cosine of 0 is 1. So 4 times the 1 is 4. And then 4 times, ultimately, this one here gives you a final value of 4 there. Okay. This one can be done in several ways. There's a longer way to pull this function apart and look at the chain rule a bit more explicitly, versus a shorter way to just do it all in one step. So let's shift the notation, because there's a lot going on here in terms of a function within a function. And if we switch it over to say y is equal to ln of cosine of pi x, we ultimately need the derivative of y with respect to x. this kind of notation allows us in future to deal with the chain rule. So the piece of the function overall that's controlling things is this piece in here. So let's let u equal that, and that reduces this kind of to two components. So now y is equal to ln of u, because you made that choice, and further to that u is equal to the cosine of pi x. And so once you've got these two, this is your sort of bridge between the two through u. And so if you can get dy du, because you can pretty easily, and if you can get du dx, then the chaining, if you will, through du allows you to pick up dy dx. That's how this whole thing works. So from the formula booklet directly, the derivative of ln of x is 1 over x, therefore the derivative of ln u is 1 over u. So that's going to be the first piece. And the derivative of u with respect to x here, well, the derivative of cosine of any function is negative sine of the function, again, times the derivative of the piece inside. That's the nature of a chain rule within a chain rule. So you've got that piece there. And so you put these two pieces together, and dy dx equaling dy du, well, that's right here, because we've achieved that, times du dx, and that's right here from the second part. And then you back substitute on what u decided, in this case, u would be, and u's all the way back here. When you back substitute and let u be equal to that, you're pretty close to the form you need now, because once you have sine of an angle over cosine of an angle, that's always going to be tan of the angle, whatever the angle might be. So there it is, done and dusted. The short term, or the shortcut way to do this, is to recognize, for example, that if you've got a function equaling ln of anything, I can promise you that the derivative of ln of any function here will be 1 over the function times the f prime of x, the derivative of the function inside there. All right, so that's kind of an algorithm that you can use. And so once you're there, you're done in very quick steps. The last consideration here was given something like y is equal to x plus x sine squared of x, over this particular interval. Can we find first and second derivatives and use those to flesh out? In green, we have so-called stationary values, because that's where the curve levels off and where the slope of the line drawn tangent would be 0. And then here's two other curves, other points on the curve, where the concavity changes. We go from concave up to concave down, hence that's a point of inflection. Here we go from concave up to also concave down, hence a point of inflection. And for the record, each of these green points are also points of inflection, because we're going from concave down to concave up. So it is possible for x values, these two green ones, to not only be stationary values, but also points of inflection. So we'll unwrap that. So the first derivative, dy dx, or just y prime, was the notation being used here. Derivative of x is just 1. The derivative of sine squared of x, the 2 swings down, times the sine of x raised to the first power, times the derivative of the piece inside. That's going to be a chain rule piece there. So classically, we set the first derivative equal to 0 to find any stationary values. And when you do that, you're confronted with having to solve this equation here, which drag the 1 over to the other side as -1. It would be great to recognize, of course, that that is just sine of 2x equaling -1. This is getting into a little bit of new territory for us, hence this kind of podcast. So one might apply the inverse to both sides. You could also rewrite this little mini equation like this. If you're in a paper 2 setting and you take this to your calculator and ask your calculator for the sine inverse of -1, it will classically give you one value. That could be problematic here because there's a lot more going on. So why don't we just back up and think of this little equation we're trying to solve as sine of any general theta equaling -1, where theta is going to be this 2x thing. Well, if you can envision the classic sine curve and how often the sine dips down to -1, well, firstly, it's -1 at 3 pi over 2, and then if you add 2 pi to that, that's the next place where the sine value would hit -1. Add 2 pi to that, and that's the next place, etc., etc., etc. So you can get a whole spread of values that satisfy the equation where the sine of the angle is -1. Well, the angle in question is really 2x, because we're ultimately trying to solve for x. This is a very general approach, and if you back substitute on the angle being 2x, suddenly you have this whole spread relative to 2x, and if you just divide both sides by 2, you start to get a string of angles that are now 1/2. So this guy, 1/2 of this guy is right here, 1/2 of this guy is right here, and what I did was consider each of these in approximate form just to help you visualize that 2.36 and 5.50. Well, there's your 2.36 in x, and there's your 5.50. So that does pick up the two, in this case, stationary values. And you can appreciate this curve keeps going, and you could actually keep going with this process to get as many as you needed. So now let's attack and pick up these red ones, which are the points of inflection, and then we'll be done. And of course, that requires you to get a second derivative and set that equal to 0 to pick up the points of inflection. Well, given our first derivative is probably better thought of like this. Again, the double angle formula is just matching up here. So derivative of 1 is 0. Derivative of sine of an angle is cosine of the angle times the derivative of that piece inside. Again, chain rule. So the second derivative is right here. Set that equal to 0. You can safely divide both sides by 2 and just consider this guy here. Again, this is in similar territory to what we just saw. So why not think about, just in general, where does the cosine of any angle equal 0, where in future that angle is going to be 2x. So we know from the cosine curve, this is a regular cosine curve, that it zeroes out here, 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 and you get the idea if you can picture the flow of the typical cosine curve. However, we're not interested in this general theta. We're interested specifically in 2x, or eventually x. So where 2x is equal to these, once again, take a half of each side, and a half of this is right here, and a half of this is right here, and a half of this is right here. And I have for you in numerical form these values here, and they correspond. You get a repeat here, right? So as it turns out, the 2.36, like we said, is not only a point of inflection, but it's also a stationary value. So the red guys match up nicely in terms of the x values here and here. You can have a look. And the green ones just continue to be consistent as well. Another way to consider something like this, I'll close it by just saying, if you can picture, and you should be able to, in red, here's your classic cosine curve, right? And we're in radians here, so it's peaking and ending at around 6.28, which is 2 pi. Well, graph transformations, you say, what does the cosine of 2x look like? Well, you end up getting an increase in the frequency because the period gets shortened. And where cosine of 2x, there we are, where cosine of 2x is actually equal to 0, you can see you've got points here, 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 and here in terms of where it's actually equal to 0. And those are the values that are unfolding here. Because if this is pi over 2, because it is, half of that's going to be actually pi over 4, which explains that. And then if this guy here is 3 pi over 2, because it is, half of that will bring you back to 3 pi over 4, that kind of thing. So it should match up. That's pretty much it. Hope it was helpful. Ciao.